Question 3. Mathematical induction. So we have to prove that this expression is divisible by 8 for all n element of natural numbers n greater than 1. Notice it doesn't say n greater than or equal to 1. So we're going to start at n equals 2. For n equals 2, that 9 to the n minus 8n minus 1, we're going to substitute 2 in, and it gives us 64, which in fact is divisible by 8. Therefore, it's true for n equal to 2. Now we're going to assume true for n equal to k, which means we're going to substitute k and say, yes, well, that's divisible by 8. Now let's go to the simplifying stage, where what we can do is we can actually take that, let it equal 8p, where p is a natural number. Makes life so much easier. So if we can separate out a 9 to the k minus 8k minus 1, later on, we can replace it with 8p, and that makes argument that much simpler. Now, for n equal to k plus 1, we're going to substitute k plus 1 there, k plus 1 there. Quite simply now, we're going to multiply that bracket out. I need a 9 to the k, so I'm going to separate that out into 9 times 9 to the k, like that. And that's 9 of them, and I only want one of them, so I'm going to have 9 of them, one of them, and then 8 of them separately. So there we are. There's 9 to the k, there's 8 times 9 to the k, giving me 9 of them. There's our minus 8k, there's our minus 1, and there's our minus 8. Now look at the red, there's our minus 8p. And we can factorize those, taking out a common 8. Well, that very clearly is divisible by 8 now. We have a common factor of 8 between those two terms. So therefore we can say that 9 to the n is divisible by 8 for n equal to k plus 1. And because it's based on the fact that we assume true for n equal to k, we now have induction. There's the first step of the ladder, n equals 2. Then we now prove that if we can get somewhere on the ladder, we can always get to the next step, and that's what we've done. Therefore, by mathematical induction, true for n element of natural numbers n greater than 1.